this, that's my output. So data in, data out. So if I need to move a triangle, this is how I move a triangle. If I need to color a triangle, I have a single function that goes out for my fragment color. And you can see it's a vector with all the different values. The colors are ranged from 0 to 1. So if you want to think in terms of functions and using arrow functions to kind of describe the operations we're doing, a vertex shader takes attributes, so whatever a list of attributes, and returns a position. A fragment shader, in this current example, doesn't have any input and returns a color, which we can have inputs once we get a little bit more complicated. So, our first example. And the screen's small, so I'm going to make our example a little bit smaller. So now our signature is going to look like this. It's going to be attributes and uniforms. So attributes are the single positions. Then uniforms are going to be uniform across everything. So if I want to give it the current time, that would be uniform across every position. So let's go ahead and do that. Actually, let's play with the position to see that this actually works. And let me define some things. So positions, so I have generate plane here, which will generate a plane. And I can show you what that looks like. This microphone's having to hold it is going to be difficult, but. So the math ahead, I'm going to create some positions. I'm going to loop through my segments, and here you can see I've got a different way I construct my geometry. So you're going to find with drawing with just code, you need to be able to define an algorithm to generate something. And this one generates a plane by doing positions and building them up, and you can see here I define triangle A and triangle B, and then I have a loop that puts them all together. Again, hand wave, don't worry too much about this, but there is a function that generates my plane for me that I write. And so here my position comes in. I don't know, can I just do this? I really don't know. Would someone mind, this is awkward, but would someone mind come sitting up here and holding the microphone for me? Like, I really apologize, but I don't think I can do the talk without. Thank you so much. I really apologize for this. So what I'm going to do is do position 2 equals my position, and because I can't modify this. And then I'm going to have my output be position 2. So what you're going to find is I can manipulate this value, and as you can see, it's going up in time. So it's getting higher and higher the more I manipulate that. Which is, okay, that's cool. But what we want to do instead is programmatically mess with it. So uniform values are the same across everything, and we have time, which I've defined. I'm hand waving over how I get this information in here. My Regal is doing that for me. But with time, I can set my output to that, and you can see now it's starting to move. So I can slow it down by doing a little bit of math of multiplication or speed it up so it just flies off the screen. Or I can start to manipulate it. So taking sines, a sine wave goes up and down as you move through it. And so if you plot that, you have a wave. Here, that wave turns into the time. And I'm going to switch up people between different things so we can share the pain of and awkwardness of having someone hold the microphone for me. Okay, so this is fun. I've now gotten a way to move my positions around.
That's pretty cool.
Thank you. Yes, you can interject things as we go through. Okay, so now we're feeding our position.x into this, and it makes it manipulate. And I can make it move faster by have more periods in the wave. Or I can, that's a really high wave, so let's make it smaller as it goes through. And then maybe we're only doing one dimension right now. It's always fun to add more dimensions to things. So instead of position.x, we'll do position.z. And now we've got a wave going through. Okay, well, so that's fun. Okay, now we've got a fragment shader. So I'm moving down to the fragment side. So this is deciding our color. And you can see here I have red, green, blue. So if I change it to green, so red and green make a yellow, and everything is white. But then I don't have any way to differentiate between all the different positions. So what I need to do is add a varying value that varies between everything. So it's my way of being able to define something up here. So we'll go back to our vertex shader and say varying, and we'll call it our V position. And it is a vec3, because everything's typed in GLSL. And I'll go instead of saying position 2, I'll just say V position, and I don't want to redefine it. I'll save to make sure I didn't screw that up. And I've defined it in my vertex shader, and I can pull it down into my fragment shader. So I'll go ahead and do that. And I will drive the red color by the X position, or maybe the Y. So now it has some depth. So now we can start to see and define how that looks. And then we can manipulate the values using math. So we can do plus 0.1, 0.2, 0.3, and start to play around with it. Or maybe we take the position for the green would be the X. And now we can start to combine the colors together to decide how to draw things. There's no correct solution here. I'm not going for correctness. There's no formal proof for what I'm doing. It's I can think about math and think about how to draw things and play around with it and just play with values. And then I can start to define things. So I can, going back up here to my wave, I can say, let's say wave height equals 0.2 instead of just 0.2. And I can start to build up a language to deal with my visualization and define those values over time. Thank you so much. You're a wonderful assistant. Give our assistant a hand. Okay, next assistant, please. I will wait awkwardly until someone comes up. Look, there's more boxes. Thank you so much. Okay, so that's not a plane. So let's get a little bit more complicated, okay? So before we had a plane that we were dealing with, and that was kind of simple to think about in terms of 2D, because you can do 2D and map it to 3D. Oh no, not a mic stand. This is too great, having people hold it for me.
Being replaced by a machine.
Automation!
We're doing our job, engineers. Keep it up. All right.
I got it.
Okay. You can call him Dennis.
This is so much less awkward. All right, let's get back to it. So now we have, what did I write here? Okay, so we need to generate our geometry first. So the easiest way to do that here is to define a box. So this is going to be more involved, and this create box function, which I'll reformat since this is easy to read. This is JavaScript. I wrote an NPM module for it. Yay, so I can reuse it, and other people can use it. So I wrote a module called Geo3D-Box, which will create our box geometry for us. And a lot of people are using it now in just kind of independent projects outside of normal frameworks. And building up this idea of simple arrays of values makes it really easy to write generic functions to do things. And so the first thing I'm going to do is create a single box, and it's going to be this box size. And so if I go back up here to box size, this magic value, if I change it, you can see it actually changes in the final visualization. And I can't dive into the source code for that, lucky you guys. But that's just one box, and I want a whole bunch of boxes to visualize. So I'm going to duplicate the box into a 3D grid of boxes, sort of like a Rubik's Cube. And I have some wonderful ASCII art here describing what I do. And I do this a lot because ASCII art is with my source code. So when I look at it later, I can define and label things and work with them a lot easier. So this function, duplicate into a grid, let's just look at everything up until the hand waving part. What I'm gonna do is I'm gonna go ahead and create a bunch of buffers to store the data. I'm gonna calculate all the positions. The normals describe the surface of it, the center of the box, where that is, how occluded it is, which is how deeply nested in the middle of it. So the values in the middle are more occluded than values on the outside boxes. And then our elements array defining how everything is put together. And you can see here's what the function looks like, right? It's a bunch of for loops, and then lots of just offsets and doing that. It's kind of like nitpicky. You have to like sit there and figure it out. It's a little bit, it takes some effort to do and some thinking, but then you can build an abstraction and then use it, and then give it magic values that can drive the visualization. So that's like a technique I use a lot. And then finally, I have a function called makeDrawCall. So it takes my instance of Regal and then my mesh that I've defined. So you can see I'm taking these complicated bits of work and encapsulating them in functions that are then easy to parameterize and use. So they end up becoming tools that I end up reusing through different projects. Okay, so this one is a bit larger of a shader because it's doing more. So feel free to have your eyes glaze over and not look at all that. But here, this is a function I've made called compute box size. And actually, I'm going to keep it close to this 4-dimensional noise function. So is time in here? Yeah, time's in here. So we can do our same trick that we've done before, the sign of the time. So now we like, okay, oh, we've inverted the, we've created a paradox and inverted it in weird ways. So, you know, if I didn't want to invert it, I'd do like plus 1.0. So that would be from 0 to 1. And then it's too big, so maybe I can do 0.5 times that to get it in a range. So I'm taking a value that was ranged -1 to 1, and now I've manipulated it to go from 0 to 1. Okay, so that's kind of helpful. And we'll go ahead and call that size, and that's a float value, so float size equals that. But that's kind of boring, like we haven't differentiated between everything. But I fed into this function, we computed the center of the box that we're looking at. And so I can take that into my function and start to build things with it. So if I take my box center, I have, this is a little mind-bending, but I have a noise function that takes 4-dimension inputs. And I can move through that. It's like a field function. I don't know, there's some math there. But it'll be pretty. So what we'll do is we'll take our, I think it takes a vec4 as input. Let's see if I can do this right. So we'll do noise equals this. And instead of feeding in time, we'll feed in the noise. So that doesn't do anything. Because I need to adjust it to where we can see the parameters of it. And I don't remember exactly what the parameters are here, so we'll play around with it a little bit. So 0.5, no, 10, no. Oh yeah, now we've got some results. So if you notice now, our boxes are starting to have some noise to them. They are a little bit different in size depending on their position. So feeding in a position into a noise function, each position is going to have a specific noise value because it's a deterministic noise. But this is a tool we're going to use. So basically, noise function, 4-dimensional value, single float value at the end. I know, like 4 dimensions sounds very scary, but. Okay. We're going to go back down to the fragment shader now. Skip around because it's hard to visualize and see what's going on. And what I've done is I've defined our color model in terms of hue, saturation, and lightness. And I can start to play around this to show what that color model will be exactly the same. So hue shifts around my values according to what color it is, so I can play with that. So if I do sign of the time, just to, there we go, flashing thing, yay. I can do saturation, so saturation changes over time. and then lightness changes over time. So, okay, let's start to pretend that we're doing a lighting function, okay? We're gonna totally fake it, because we've computed when things are occluded. So if I give the lightness to be just the occluded value, you can see as things go in towards the center, they look like they are darker. This is not actually simulating reality. I'm just taking some of these values I've pre-computed and thinking, oh, if things are in the middle, like they should probably be darker. So I can think kind of artistically with the tools I have. And that, I'm gonna just adjust the values to be a little bit different. So now occluded kind of looks like it's lit just a little bit. And maybe I've got V position. I've got the position of the point. Let's feed that into hue. So position.x. Now I've got a multicolored thing. And then maybe I'll do V position. I don't know. I'm making stuff up. There. It's a pretty rainbow thing of boxes. Okay, so now we can see what we're doing, but let's make it fly around and move a little bit. So we'll go back up to our compute box size, and we've got, let me break this down into more lines so we can see what's going on easier. So we've got a 4-dimensional vector. The first vector, the 3-dimensional vector box center we have right here, but we've got this 4th component we haven't used. So of course, let's throw time at it. So now we have a noise function that is driving the animation. And what we're doing is we're taking a slice of the noise function and then moving through it in a 4th dimension, which sounds really cool. I like saying that. That sounds fun. I don't know what that means, but that's what we're doing. But looking at this, I mean, thinking in terms of I've been programming performance tooling all day. I have an hour, and I still have some energy left at the end of the day. Being able to start to find things and play around with them and look at the math I've learned, and express that creatively, I think is a lot of fun. And then building up the tools, you can see we've ramped up our complexity. Imagine coming into the talk right now and seeing this. You'd be like, whoa, how do we get here? But now there's some logical steps we've taken. We've created triangles. We've created geometry. We've done some weird things with 4-dimensional noise. Okay, but you can build up those tools and then start to put them together in kind of an interesting way. And then also, I think I have some of the other assets I've done on other things. So you'll see a lot of dust in my scenes because I think it makes it seem ethereal and interesting. And then I found a way to make the background boxy as well, and now we have this kind of interesting boxy thing that we can see. And so starting with one component, you can build up others, and then I reuse the background on this. And a lot of my code is, it's really liberating to be able to copy and paste and throw away. So most of my code for all this is copy and pasted. There's not many modules that come out of it that it's reusable. I don't try to create some big abstraction. I just try to create something that's useful. Okay, number 3. Okay, we've got this weird box thing. The lighting, I've already pre-applied some lighting to it. And it looks a little weird with the way it is right now, but you'll understand why I chose that lighting model. So far we've been using triangles as our primitive, and I said sculpting with algorithms was part of the name of the talk, and the reason for that is that I can actually find a set of tools I can use to define operations that are in terms of a sculpture. And so the way I do that is instead of using a triangle, I'm going to define it in terms of a quad. So A, B, C, D for 4 points, and define it that way. And it's just it's an abstraction where at the end of the day, I'm packing all this information to buffers. So I can define my geometry however I want, as long as I have just the memory at the end of it. And having done 3D modeling and art stuff, I would use tools like this, but I was trying to think, how can I make these tools programmatically? So for this one, what we're going to concentrate is this create geometry function. And you see this create, so I have a quad library I built that I started to reuse. And I have this function called create box, which if you look in the implementation, it defines that kind of box relationship. And I can, again, drive it with parameters here. But a really cool property with quads is that there's this algorithm called Catmull-Clark subdivision. And I wired someone else's NPM module into my own module and then hooked that in so I can start to subdivide. So you can see here I've done 1 round of subdivision, and then 2 rounds, and 3 rounds. And then if you do too many, it ends up being slow and might crash my browser. So I don't want to, well, not crash it, but make it really slow for a little bit. And it'll say, this script is slow. Would you like to stop it? Yes, please. So now I have a way to turn a box, which is kind of like now think in terms of a metaphor of working with clay. You've got your kind of raw form, and you want to start to manipulate it. So I need some tools to be able to do that. So I wrote an extrude function. And extrude takes a mesh, which we've defined up here. It takes a single cell, so a single quad, and an inset percentage, how much to inset, and an extrude length. So actually, let me comment this out and go back to box mode or comment that out. So we've got a box, and we need to fill in all these things. So I haven't defined these yet. So my cell will be, I'll take my mesh cells and take the first one arbitrarily, and then a inset percentage. I'll do 50%, and then an extrude length, which will do 0.1. So that's kind of off the screen a little bit. Do less. So you can see here I've taken that geometry and popped it out a little bit. In fact, if I do this one, I can change it to lines. And the screen's a little small, but you can see the lines that go into this operation. Revert that. Okay, so one small extrusion is, where'd I go? One small extrusion is not very interesting, but I can think in terms of looping and iterating over things. So I'm going to create a for loop with, let's say, 4 iterations, and then take that same thing and run it again. And so now I've created this weird little wobbly thing, I don't know. And then let's see what happens when we start to subdivide that. Okay, something's happening here. That's weird, doesn't look great. Maybe I should get another cup of coffee and try it again tomorrow or something, I don't know. But right now we're just running it on one cell. What I could do is take all of my mesh cells, and we'll call it cells, and I'll go ahead and slice it to get a copy of my cells. Since I'm going to be manipulating them, I want to take the original list of cells. And I would go cells, for each of them, I'll take a cell. And then run that. So you can see now I've got, okay, that's weird. Still not great. Now I've got this spotty, bumpy thing. Well, maybe we can do something else interesting. We'll leave that subdivided. Let's go up here and subdivide before we do that. So we'll subdivide once. Now we've got spiky ball thing. Now it's starting to look cooler. Nice. And it's not quite spiky enough, so maybe I will do 0.202. Now I've got a really spiky thing, yes. More spikes. Let's subdivide again. Oh, there we go, nice. So now I've got some weird spiky thing, but it's too even. Generally organic operations. So this is starting to look more like cellular biology, which is a subdivisional process where you have iterative things happening at a scale. So it quickly starts to look organic. I don't know exactly what I'm doing here. I'm just playing around with this idea of subdivision and extrusion. And by the way, building out this library, I didn't have all these operations. I would start building one small thing and add one operation until I had like 20 operations and had a big tool set. But it was a small iterative process. So finally, let's see if I can do one last thing. I have a utility function to rotate a single quad. And I wrote this already, so, oh, this does my extrusion for me. Trying to decide if I want to try to wire that up. I'm not. But looking at like finished pieces, let me zoom through. That's actually the basis for this one right here. So I walk through the process. If you imagine like going through and rotating them and adjusting the frequency and size of it, and then I have a little bit of rotation, rather than just doing like, hey, cool demo, bro, try to make it a little bit more artistic by like changing the background color, making it a little bit nice and aesthetic. I try to make the background look like it's blurred so that it gives the sense of a microscope zooming in on something, and maybe this thing is sitting in some fluid and it's got dust going around it, so it makes it a little bit more ethereal. So after doing the step of experimenting with some kind of operations in space, come up with a way to visualize that to make that feel nice and interesting. So I do this for fun. I enjoy it, and it lets me explore lots of math concepts and different algorithms and geometry, which I find really interesting. And so after talking about this, people a lot of times want to know, like, okay, like, how do I do that? Where do you start? So getting into graphics, I would say the number one thing, if you're interested, is be prolific. Make lots of things. Don't make one big thing, but be prolific and make lots of things, throw away and iterate very quickly. I think that's important, because if you concentrate on making your one big game, you're gonna make lots of very bad decisions at the beginning. But if you are prolific for a year and create all kinds of tools and knowledge on how to build something and then make your big game, then that is, I think, a more successful model. 3D is a lot more math, and so do something in 2D first. It's a lot easier to learn 2D and understand 2D, and then you can take that and then take your understanding and knowledge and ramp up into 3D. And like I said, don't overinvest in a monolithic game. Save that. Save that for when you've learned a little bit more. As far as 2D tools and community, I would recommend, the easiest is Canvas 2D, this for the web. It is a dead simple API. You can start drawing and playing around with it. So if you want a challenge, we saw how to use a sine function. Try to build something that plots a sine function. This is a great activity. And then take your thing that plots it and then add more sine functions and then more sine functions and then see like how much can you make it warble, then add more dimensions to it. It's a great way to play around and learn it. And I would suggest investing in a community. Like there's D3, which is for like has tons of knowledge and information on data visualization. Pixie.js and Phaser.js, if you're into more gaming and kind of the old Flash scene, I think has moved there in many ways. And processing for kind of, a lot of people think algorithmically there. It's interesting. 3D tools and community, 3JS has tons of great stuff. What you saw me do here was I wanted to remove as much of the framework as I could and just get down to the math. I don't recommend that as a starting place. So 3JS has a great active community, lots of examples. Unity has lots of like amazing tools that you can even target the web for. It has tons of people working in that space. And the one I'm using is Regal, which is a smaller community. Kind of similar folks in the kind of browserify space are working there. And it's more of handling a lot of the like nitty-gritty WebGL stuff for you. So you can write and do crazy things with it, and then the WebGL API doesn't get in the way. And it's declarative and kind of functional, so it feels nice for the way I like to program. And as far as learning, if you want some resources, Trig for 2D, it's been a while since Trig or you didn't ever take a Trig class, that's kind of 2D, which the math you need. Matrix math for 3D, I'd recommending just getting on Amazon or something and get a book. If you want to do shaders, which we've been writing shaders, the book of shaders is a great resource. And also, if you liked me rambling about my own process, I do that on YouTube as well. under Tatum Creative. So you can find me there. I'm going to do all these as videos, so if you want to watch them again and like follow along or play around with the source code, eventually I will break this out into a series. And finally, where to find me? I'm on the web in different places, so if you want to follow along with my escapades, I'm there. So thank you all so much. Are we done? Do we have time for questions, or should I wrap up? Okay, 5 minutes. Questions? So what do I use these for? For fun, and I mean, it's a little bit self-promotion, I guess. You know, like here I am, like it's hard to say I'm great. I know what I'm doing when I'm programming. It was honestly really useful applying at Mozilla, and then going for like that. The person who worked on like some cool project and knows a ton of stuff is quizzing you on stuff, and you're like, check out my ray marching algorithm. It's fun and pretty. That was really nice. But really, it's about my passion and why I'm programming. I think that's the ultimate reason, because I want to know how the world works, and programming lets me model that world and lets me model math and my understanding of it. So I've done things that, like, I've built an evolution simulator. Because I was curious, people tell me this is how it works. Let me like program that and model it. So I find it really interesting to do that. There are jobs and actual practical applications to a lot of this stuff. I just choose not to do that. I choose to write code that it's very freeing to say, I'll just mess around and see what I'm gonna make a squid and it's gonna be fun. So that's my personal tale of like what I'm using it for. Oh, it's Atom. I have Atom editor, and then I'm using the build stuff is all Browserify with Budo, which is a live reloading server, and it's a really I try to keep my build situation really simple. So I save, it refreshes. I actually work like this when I'm doing. Usually, I actually have the dev tools open as well, so I can catch any console messages. But my workflow is usually like go to a cafe or like late at night sit on the couch and have my editor and my visualization there and start with something and then just save and refresh and build on it. So that's my process. Budo. Yep. All right, well, thank you all so much.